that where we don't have answer key in the exam hall to somehow manipulate. It's no marks for the steps, am I right? You got to find. That's why answer key is wrong. Official answer key only. Okay, official answer key only. Okay. Now I have already solved it. Okay, I think it takes a lot of time. Like this is a YKLM problem, the Princeton question. Okay, the question is like this. You can see here. Okay, two uniform rods of length 1 meter. He gave length 1 meter. He took length L and L. Okay, fine. He took length L and L here. Okay, fine. So connected to a frictionless hinge. Okay, this is the hinge. Okay, this is the hinge here. Okay, it is connected to frictionless hinge. Okay, fine. The hinge is held at height. Okay, it is held at height. Okay, so it can rotate this one. Okay, fine. This hinge. Okay, so it is held at height, and other end of the rods rest on a frictionless plane, such that angle between the rods is 2 pi by 3. What is 2 pi by 3? 120 degree. If it is 120 degree, then this must be 30 degree, 30 degree. Okay, fine. 30 degree, 30 degree. Now it becomes exactly same as that Weichel problem. Okay, he also started with the same initial condition. If initial conditions are changed, your answer will change. Okay, they can manipulate the question. Okay, the hinge is released from the rest. It is not pushed here. Okay, it is just released so that it will slide and this hinge will hit the floor. Okay, that's the question. Okay, fine. Release from the rest. What is the speed of the hinge when it hits the floor? Okay, that's the question. Okay, now what I do is, again, it may take again half an hour to solve using Lagrangian idea. I'll apply again conservation law. Okay, fine. So you do one thing, you just go through. This is rigid body related Lagrangian problem. Okay, in that one last video. Okay, this video. Okay, so try to solve this one. This is the only problem. Okay, where I have defined the coordinate, and from the coordinate I have defined the kinetic energy. This is the only problem. Okay, suppose if I define this angle as theta here. Okay, so these are rigid bodies. Okay, these are rigid bodies. Okay, you have to write motion of center of mass, motion about center of mass. Okay, I took x-axis here, y-axis here. Okay, wait a second. Let me define at least Lagrangian. You try to proceed further. Okay, fine. Is that okay? Suppose this is my center of mass. Are you guys with me on Google Meet? Is that okay? Now, suppose this is the center of mass. I mean, potential energy is very simple. Am I right? I mean, if I take this one as my zero potential, V equal to 0, mg into height. Okay, fine. Suppose each of them have mass m, length L. Okay, each of them have mass m, length L. Okay, then potential energy that's equal to mg. Okay, what is this one now? This height. If the whole length is L, this is L by 2. What is this height? L by 2 cos theta, L by 2 sin theta, isn't it? Fine. L by 2 sin theta. Or what I did is, okay, I found I have written the locations actually. Okay, I wrote this one as suppose x1, comma y1. Fine. This one as x2, comma y2. You got my point. Locations of center of mass. Okay, for motion of center of mass. Motion about center of mass, again theta only playing the role. If you think properly, then I can quickly write that one. Okay, for motion of center of mass. Okay, what is this one? That is mg, height is y1. Am I right? Okay, now I'll write that x1. If I take this one as the origin, what is x1? Okay, wait. I need to. If this is theta, x1 is this much. Am I right? What is this x1? L by 2 cos theta. Am I right? Fine. X1 is equal to L by 2 cos theta. No, minus negative sign. Okay, it is in the negative axis. Okay, x1 is equal to minus L by 2 cos theta. What is y1? Y1 is positive. Am I right? Fine. Y-axis is positive. Okay, fine. So y1 is okay L by 2 sin theta. Okay, fine. Oh, someone is joining. Fine. I mean, you learn this one also, okay? I mean, for Lagrangian mechanics practice, okay? X2 is equal to what is this one? This is also theta. What is this one? I need this much, am I right? This is X2, L by 2 cos theta. Fine, L by 2 cos theta. Okay, Y2 is equal to L by 2 sin theta. Okay, fine. So this is the only problem where I have defined the coordinate. Then I mean, theta is the generalized coordinate. Only theta is sufficient. Only one generalized coordinate is sufficient. Only theta is sufficient. Okay, fine. I mean, because of symmetry, these two thetas are same actually. Okay, I mean, you can express everything in terms of that theta. Okay, now you see this one, V equal to what is this one? Mg y1. Okay, fine. Mg y1 plus Mg y2. Can I say like this? Okay, potential energy of this one and this one. Okay, while writing potential energy, we think like whole mass is focused at the center of mass, and we are going to write the potential energy. Okay, I mean, that is by taking this x-axis as, okay, so zero potential. Okay, so that is actually 2 times, okay, mg, what is y1 equal to y2 equal to L by 2 sin theta. So L by 2 sin theta. Okay, so that's equal to what is this one? Mg L sin theta. That's the potential energy. Very simple. Okay, but kinetic energy is challenging. Why? It is a rigid body. It contains motion of center of mass, motion about center of mass. So that's why kinetic energy of motion of center of mass, okay, plus kinetic energy of motion about center of mass. Okay, fine. So now motion of center of mass, okay, when you see this one, that is nothing but again you have to use this Cartesian coordinate only, center of mass. Again, that Cartesian to polar, we have already transformed here. Okay, motion about center of mass. Can you quickly think? If you are sitting at center of mass, okay, theta is the angle which defines motion about center of mass. Is that okay? Fine. So when I mean the best way is, okay, look into this one. If a rod was like this here, you are sitting at center of mass, you are looking horizontally in this direction. Rod was inclined with an angle theta. Okay, fine. Now if rod, okay, falls on the floor, okay, you are at center of mass, again you are looking horizontally this direction. Okay, now theta is 0. That theta only will define motion about center of mass. Okay, that realization you should quickly need. Okay, so that's why kinetic energy of center of mass is equal to half, okay, can I say m into uh, VCM of first rod, the square, plus half. So can I say like this? Kinetic energy of center of mass of this one. You have two rods here. Okay, fine. Can I double it? You can double it also. Okay, fine. Plus half m, okay, VCM of 2 the square. Okay, fine. So half, okay, I omega square. Okay, that omega is theta dot only. Got my point? That omega is theta dot only. Okay, now what is I? When you go and sit at center of mass, now rod look like moving about center of mass. Okay, about an axis passing through center of mass perpendicular to the rod. Okay, length of the rod. What is that? That is ml square by I is ml square by 12. Ml square by 12. Am I right? About the middle of the rod. Is that right? Okay, fine. Ml square by 12. Okay, these things you should grab. Now I mean, in Lagrangian approach, okay, I will convert these things also in terms of theta. Okay, only one generalized coordinate, and let me, I mean, we can solve further. Okay, you see this one, half m into what is this one? This is x1 dot square plus y1 dot square. Fine. Is that okay? Because x1 dot y1 dot are location of first center of mass. Okay, plus half m into x2 dot square. Ml square by 12 or 3. What happened? Here also 2 should come. Am I right? That's right. Into 2. Am I right? Into 2. That's perfect. Okay. Here also 2 should come. Is that okay? So now you see this one. Okay. Half m x2. I mean, or I can multiply this one by 2 if you are okay with that one. Isn't it? Half m x2 dot square plus y2 dot square plus what is this one? That is I omega square simply. Fine. I mean, because you have two rods, okay? I mean, motion about center of, or the whole thing you can multiply by 2 actually. Okay, fine. Whole kinetic energy term you can multiply by 2. Okay. Half I omega square into 2. Okay. Or I can cancel out that 2 here. Okay. Now what is this one? X1 dot square plus Y1 dot square. Can you see? Cos square theta plus sin square theta will come. Can you do this one? X1 dot Y1 dot. Okay. When you square and add, what will you get? What is X1 dot? This is equal to, I mean, what is that? Minus L by 2 sin theta, theta dot. Y1 dot is L by 2 cos theta, theta dot. Am I right? X1 dot, okay, minus L by 2, minus plus will happen. Okay, plus sin theta, theta dot. Okay, when you take the derivative, this one, okay, Y1 dot cos theta, theta dot. Okay, when you square and add, what will happen? L by 2 square, theta dot square is taken outside, sin square plus, I mean, you got a point. Fine, X1 dot square plus Y1 dot square, that's equal to L by 2 the square, theta dot square common, sin square theta plus cos square theta. Okay, so that's why your kinetic energy is ultimately, okay, so 2 times this one m into, okay, what is this one? Half will go here. Okay, what is this one? L 1/4 of L square theta dot square here. Fine, L square theta dot square. Okay, here also 2 is gone. Okay, what is this? 2 is gone. M L square by 12 actually. What is omega square? What is omega square? Theta dot square. Fine. Now can you take LCM? What will you get? One third of 1/3. 1/4 plus 1/12. 12. 1/3. 1/3. Okay. 1/3 of L square. Oh, M where I left M was here. Fine. M here. 1/3 of M L square theta dot square. Okay. Either okay. 1/3. 1/3. Yeah, that's right. Okay. 1/3. Okay. Fine. And this one is also right. This is the potential energy. Now, I mean, I will not proceed further. Now, Lagrangian is defined. Okay, initial condition is taken. Lagrange's equations of motions are written. Okay, that is quite a lengthy step actually. I don't think they are expecting that one because in JEST exam, sometimes they expect a lengthy step. I mean, maybe in that Princeton question, they were expecting Lagrangian approach only. Okay, but when I see that JEST and TFR question, most of the case they don't expect us to do much lengthy step. Okay, that's why let us apply conservation law only. But to apply conservation law also, you should have clear-cut idea. I mean, it's a rigid body. You always have motion off center of mass, motion about center of mass. Okay, fine. Is that okay? You do further step. Okay, because what if they ask what is the Lagrangian or they giving some other initial condition? Okay, fine. And define the problem. Okay, that approach may be superior. Okay, Lagrangian approach. Okay. Now, but what I do now is, okay, what I do now is, okay, I mean, so for exam, okay, let us not he's asking, this is released from the rest when it hits the floor. Okay, what is the speed at which it is hitting? Okay, fine. So that's a question he has asked. Okay, now I'll just forget about everything. Okay, I'll just, okay, I'll first write the potential energy. Okay, what's the potential energy? Okay, he gave initial angle also. Am I right? 30 degree. 30 degree initial angle is also given. Can I find initial potential? I mean, energy is conserved. Okay, potential energy plus initial potential energy plus initial kinetic energy is equal to final potential energy, final kinetic energy. Finally, once it falls on the floor, there is no potential energy. Center of mass will be on V equal to 0. Okay, that's why initial kinetic energy equal to 0. Okay, initial potential energy is equal to what is this one? I mean, can I write directly? What is this one? mg L L by 2 sine theta, but added one more time, okay, sine 30 degree, okay. That is my initial kinetic energy and potential energy. Finally, potential energy is 0, okay, fine. TF I need, okay. So VF equal to 0, okay, fine. Now I will equate addition of these things, okay, energy, okay. Then I will try to find the final speed, okay. But when you write the kinetic energy, okay, once it start falling, okay, once it start falling, okay, when you write the kinetic energy, again it contains kinetic energy of motion of center of mass plus kinetic energy about center of mass. About center of mass. Is that okay? Fine. So while writing kinetic energy of center of mass, you are locating this one, am I right? Like, I mean, if I dim these things, oh, yeah, let me keep it as it is, okay. I'll just draw it like this. Am I right? I mean, like you are tracing this one, isn't it? I don't know how it moves. It may move on arc actually. I feel like this. What do you think? That center of mass moves on arc actually. I feel like this, isn't it? When it falls, not like this. Maybe it moves on arc like this. Is that okay? Now this is the velocity of center of mass. Okay, maybe like this. I feel so, isn't it? How do you argue? I mean, you can see the x1 dot y1 dot. Okay, you can argue on the basis of x1 dot y1 dot. Okay, fine. So now I have to write it like this. Okay, 2 times. Okay, half m into velocity of center of mass the square. Okay, plus 2 times what is this one? 2 times. Okay, half I omega square. Okay, half I omega square. Okay. Now whatever v here. Okay, you see this one. That v is velocity of center of mass, not velocity of hinge. So don't you feel when it falls, hinge will hit with more speed than center of mass? This won't hit the floor at all. This is already on the floor. When you move in that side, suppose you think like one rod is just falling, that end of the rod will hit the floor with higher speed, isn't it? Fine. Hinge will hit with actually double speed of center of mass. Okay, because when you see the length ratio. Okay, fine. Anyway, I'll argue that one. But whatever speed is coming here, okay, I will keep that speed. I'll keep that speed as it is. Okay, initially that speed was 0. I'll keep that speed as it because he's asking speed over there. Okay, but that speed is speed of center of mass, not speed of the hinge. Speed of the hinge is double of that one, and he's asking speed of the hinge in the question. Am I right? Fine. With what speed? When speed of the hinge when it hits the floor. Okay, he's asking about hinge only. Okay, fine. So be careful with this one. Okay, this is where I mean, uh, everyone made the mistake actually. Okay, what I'm saying is, okay, this is a center of mass speed. Okay, fine. I'll keep it as it is. I don't have to elaborate, but I need to convert this one also in terms of VCM. You got my name. I need to convert this part also in terms of VCM. Then again, I got that one. I got my answer. Like initial energy, final energy, you equate that one, you can solve for this VCM, you can double it, you will get the speed of the hinge. Is that okay? Now, how do you write this one in terms of like VCM? Can you think of it? Hmm? Hmm. I mean, you can apply that one. Like, what is that VCM square? This is your VCM square, am I right? Fine. I mean, here also you can do. Okay, but I mean, I don't want to go for this one. I want to handle there only. Like, I mean, I'm thinking just like I'm in the exam hall. I don't want to elaborate much. Okay, here you have this one. Okay, this is your VCM square. Am I right? Okay, and you have your half I omega square. If it is VCM square, okay, fine. Then this one only. Okay, check this out. Okay, uh, half I omega square. Okay, that's equal to half. Okay, ml square by 12 into theta dot square. Okay, in this one, what I do is, okay, half into L square by 4. That means m by 3. Am I right? 3 into 4. L by 2 the whole square. L by 2 the whole square, theta dot square. You got my point. I'm writing this one and again in terms of VCM because I need VCM ultimately. I mean, this is my old approach, but I will have better approach. Okay, quick approach. Huh? Now, yeah, that's right. What I'm saying is now this one half of, okay, m by 3 into this is again VCM square. Is that okay? That's again VCM square. Okay, that means half I omega square, half of m by 3 VCM square. What is it? Is that okay? Half of m by 3 VCM square. Okay, fine. Half I omega square. Okay, so 2 times half m VCM square. I don't have to use the vector. 2 times, what is this one? Half of m by 3 VCM square. 2 got cancelled. 1 plus 1 by 3. What is this one? 4 by 3. 1 plus 1 by 3, 4 by 3. Okay. Isn't it? 4 by 3 m into VCM square. This should be worked out carefully. Okay, suppose if I haven't compared with my that coordinate idea, how would you write this one in terms of VCM? Are you getting my point? How would you write this one in terms of, I mean, here I have used coordinate idea, then I have compared and somehow I have written that motion about center of mass also in terms of VCM. You see this one carefully. You see this one carefully. Okay, if you suppose take this is your, I mean, this is bit rotated actually, am I right? Instantaneously. Okay, fine. If you think like this, if you apply your S equal to R theta formula, fine. S equal to R theta formula, then what will happen is, okay, L by 2 will come, am I right? L by 2 theta actually. S is equal to L by 2 theta. Okay, S dot, that is my VCM. That's equal to L by 2 theta dot actually. If I take that this is my point about which it is rotating or something, it is L by 2 theta dot. I'm locating VCM, I'm not locating hinge. Okay, hinge I will take care later. Okay, hinge I will take care later. Okay, that is where the mistake happened. Okay, fine. Are you getting my point? I mean, if I take this is my axis of rotation, if it is falling, okay, if it is rotating, okay, speed of the center of mass, okay, I'm applying that. Suppose if it is has rotated by, sorry, if it has moved by s distance, okay, fine. I'm applying that one. Okay, s equal to L by 2 theta or something. Is that okay? Fine. So I mean, even if you apply that one, okay, what would you get? Half m L square by 12. Okay, theta dot square. What is that theta? What is that theta dot? VCM by L by 2. That's equal to half of m L square by 12. What is this one? VCM square by L by 2 the square. You end up with the same thing. Is that okay? Fine. This half I omega square. I'm working out half I omega square part. Okay. VCM is equal to L by 2 theta dot. That you should grab. This is the main equation. Okay. L by 2 theta dot. Okay. Then my half I omega square, that happens to be equal to this one. Fine. Half I theta dot square. I'm substituting for theta dot here. Okay, fine. So you end up with the same thing. What is this one? 4 here, 4, 3 the 12. Half of m into 1 by 3rd of VCM square. You end up with the same thing. Half of m by 3 VCM square. Somehow your kinetic energy, in terms of purely in terms of speed of center of mass, not speed of the hinge. Now I will equate them. Okay. Now I'll equate them. Is that okay? Initial potential energy is equal to my final kinetic energy. Fine. And I will find VCM. Okay. So now, I mean, now you can grab the idea. Okay. Fine. I mean, this point will hit the floor with nearly double speed of this point. Don't you feel that one? This point is not hitting the floor at all. When you move along, again, you can apply what is that V equal to R omega kind of formula. Omega is same. Okay, fine. If you apply V equal to R omega, V equal to R omega. If omega is fixed, V is proportional to R. Am I right? If you feel like it is rotating, okay, if omega is fixed, okay, rotational angular speed is fixed, okay, speed on the rod. Are you getting a point? Like if I have a rod, if it is rotating about this axis, okay, speed at any point, okay, so that depend, I mean, that is proportional to this R actually. You got my point? Fine. That's why hinge will hit the floor with nearly double the speed of VCM. That is very sure for me. Is that okay? Fine. So see this one. Now I will 4 by 3 m into VCM square. That's equal to what is the initial potential energy? Mg L by 2. L by 2, isn't it? MgL whole divided by 2. M got cancelled. Okay. L is simply 1 meter. Isn't it? L is simply 1 meter. What is VCM? VCM equal to root of 3G by 8. I'll write one more step. Square is equal to 3GL divided by 8 here. VCM, that's equal to under root of 3GL by 8. Is that okay? 3GL by 8. Okay. That is equal to, I mean, since L is equal to 1 meter, G he has mentioned it as 9.81 meter per second. Can you find this one? 1.91. But this is not the speed of the hinge, this is the speed of center of mass. Is that okay? 1.91. That is the answer key, but that is wrong. Is that okay? Fine. So now you can apply this idea. Is that okay? If you think like, so I mean, even if you are not going to that rotational one, okay, you think like you have a rod, okay, which is falling here. Fine. I mean, this is already on the floor. Okay, fine. This part is already on the floor. When it falls, obviously this one will hit the floor with less speed. This one will hit the floor with nearly double speed only. If you apply this idea, that's better. Okay, fine. And that matches with a speed of hinge. Okay, that's equal to double the speed of center of mass. Is that okay? Fine. So that is what is that? You just write that one. Okay, 2 into root of, okay, 3GL by 8. Okay, that's equal to, I've explained it. Okay, in the Lagrangian approach, 2, if 2 goes inside, it will become 4. Okay, 3GL by 2 actually. Okay, that's a Vicalium answer also. Same initial condition, everything is same. Okay, fine. Now if he manipulate this question, you got my point? This is not the answer. Okay, you have to double it. Okay, if you double it, what is that one? 3 point. Can you double it? Fine. 3.8 meter per second. Okay, that is the right answer. Okay. I mean, when I saw the question, I quickly plugged it into Vicalium answer. That gave me this one. Okay, that was not matching with the answer key. So I was thinking like, I mean, there may be some mistake in Vicalium approach. No mistake. Okay. So, but the mistake here actually. Okay, here it is a speed of center of mass, not speed of the hinge. Is that okay? Fine. And if you can write this one also logically, here theta dot comes, am I right? If that theta dot also, if you write in terms of VCM, you don't have to go to this much coordinate idea. Whatever coordinate I have taken, you don't have to go to that one. Got it? Find that angle, whatever I have defined. You don't need this much idea. Okay, fine. So I mean, what I'm doing here is, okay, fine. What I have tried to do here is, like, I was thinking, like, okay, momentarily, okay, fine. When the rod is falling, L by 2, okay, L by 2 theta, L by 2 theta, okay, or changing theta. Can you select that? Okay, fine. I better to say uh, delta S of center of mass, okay, that's equal to L by 2 delta theta, delta theta. That is right edge. Change in the location of center of mass. Distance traveled by center of mass, can I say like this? Fine, here. There is L by 2, okay, into change in theta, not full theta, okay? I mean, this full theta is defined like this, am I right? If you apply S equal to R theta, you have to apply it like this actually, okay? This is the right one, okay? I mean, now let me try to this one. This rod, okay, fine, it has moved like this, okay? Then my center of mass is moved by angle, I mean, this is my delta S, okay? It is moved by this one. This is my delta theta. You got my logic? Whole theta is defined with respect to horizontal. This is change in theta. Okay, change in the location of center of mass. Okay, the relation between them is L by 2. Is that okay? Fine. Now this only gives me, if you divide by dt, delta t, okay, what is one? VCM, that's equal to L by 2 theta dot. Okay, L by 2 theta dot. Okay, fine. This is very important one. Try to analyze that. Fine. Now, if he suppose gives some different initial condition, if he suppose pushes this one, then you have initial kinetic energy also, along with initial potential energy. Okay, fine. That kinetic energy should also be used. Okay, fine. At whatever the situation, okay, speed of the hinge, okay, that is double the speed of center of mass. Okay, even if you change the initial condition, you can solve it. Change the initial kinetic energy. Okay, fine. Solve it one more time. Is that okay? But whatever Wykelim has done, okay, it is required in some other problem, okay, that differential, the way that he solved the differential Lagrange's equations of motion. Okay, after this one you write Lagrangian, am I right? Fine. So kinetic energy is this one, potential energy is mgl sine theta. Then he will write Lagrange's equation of motion. From the Lagrange's equation of motion, whatever how he found that final speed, okay, that is very nice to work out. Okay, you work out that one. Okay, it is required somewhere else also. Okay, fine. Any question quickly? Is that okay? I think the difficult, I mean, this one, this half m into VCM square, okay? Motion of center of mass, motion about center of mass. Connecting this one to VCM, okay? That is what you need to think geometrically. That after that one, your final answer is velocity, speed of center of mass, not speed of the hinge. Speed of the hinge is double of speed of center of mass. Is that okay? Fine. That is also required. Is that okay? Don't compromise with anything. Okay. If answer keys are wrong, fine. Okay. Any question? Quickly. So shall I move on? Check this out. Solve it again. Okay. I mean, official answer key is 1.91 only, but that is not the one. That's okay. That is the speed of this center of mass. Okay, but speed of the hinge is larger. Okay, keep that one in. I have taken two factor. Am I right? Have I taken factor 2? Taken factor 2. Is that okay? Because you have two rods actually. Okay, fine. So I taken factor 2. Okay, everything is right. Fine. So shall I move on?